my channel. Hope you're enjoying the videos. So first of all, we did the states of matter for O-level chemistry. I covered actually about everything that is in the chapter. Now we'll be moving on to experimental techniques. It's actually a very useful chapter when it comes to P4 or ATP, but it is equally important for your P1 and P2 as well. So let's get right into it. So first of all, we need to know what substances are we dealing with in this chapter. For example, there are two types of substances that we actually have in our syllabus or in general in whole of chemistry. One is a mixture and the other is a compound. All right, so first there is a mixture and the other is a compound. Now you need to know the differences between them. For example, let's just say this is a chemical reaction that occurs. All right, this is nitrogen, this hydrogen, and forming ammonia, a very famous reaction known as Haber's process. We'll be learning it in great detail in upcoming chapters. All right, so I've not balanced it, but in general nitrogen bonds, the bonds between nitrogen are broken, then the bonds between hydrogen are broken, and bonds in between nitrogen and hydrogen are formed. It's generally how it is. And on the other hand, we have water and we add NaCl, for example. Now the resultant mixture, it will be the resultant solution will be a mixture, right? So what is the difference between them? So first of all, let's see the differences between a compound and a mixture. All right, so first of all, let's see a compound. So compound is actually a pure substance. What does that mean is that it only contains one type of particles. Any substance that contains only one type of particles will be a pure substance. What actually does that mean is, for example, this is a container and I say that ammonia gas, this NH3, is present in it. What I mean, and when I say that it's a pure substance, what actually is that? What does that actually mean is that, for example, this is a molecule of ammonia, this is a molecule of ammonia, this is a molecule of ammonia, this is a molecule. No other substance is present. All right. But when I come here to NaCl, actually, and I say that this is the beaker. So first of all, there will be water molecules. All right. Then there will be sodium ions. Then there will be chlorine ions, and of course there will be hydroxide ions. There will be H positive ions. I'm very sorry for the messy drawing, but you need to deal with it. All right, so this is all that would be present inside a mixture, but here in the compound you only see one type of particles, that is the molecules of ammonia. Now some students have this confusion that, well, the ammonia molecule has two types of atoms, but when these atoms are combined to form one molecule, that we will say that one molecule is one particle, right? Because it contains the characteristics of ammonia. Hydrogen separately and nitrogen separately do not contain the characteristics of ammonia, but when they are combined in form of a compound, they do contain the characteristics of ammonia. So we only say that a molecule of ammonia is one particle. We do not consider H, 3H and 1N, four separate, two different types of particles or four separate particles. These are one particles only on the molecule of ammonia. So compound, they are pure substances. All right, and because why are they pure substances? Contain only one type of particles. Only one type of particles. Great. Now, on the contrary, mixtures, they are impure substances. Impure substances. Now, what does that mean? Contain more than one type of particles. More than one type of particles. Great. Now next, oh sorry, this is supposed to be one. Okay. Now next, when it comes to compounds, now the compound will not contain the characteristics of its constituent elements. What does that mean is, for example, I have nitrogen and hydrogen, a mixture of nitrogen and hydrogen in one gas jar, and ammonia gas in the other one, in another gas jar. Both will not show the same. Both will not show same chemical reactions. They will show different chemical reactions. Why? Because they are two different substances, and ammonia will not contain the chemical reactions of nitrogen and hydrogen, right? It will not show chemical reaction of nitrogen and hydrogen. So what we say is that the compound has different characteristics from its constituent elements. And these contain the same properties as their constituent elements or substances. Same properties as constituent substances. Now I'm using the word substances here instead of elements, because there can be a mixture of compounds as well. All right, and it will show the characteristic properties of the compounds. All right, I'll explain that in a minute. All right, the third particle, the formation of compound may be reversible, or irreversible. But the formation of a mixture is always reversible. I can always get back the constituent substances back from a mixture. Always reversible. And it is this point that we'll be studying in great details in this chapter. Alright, let's move on to the fourth property. The constituent elements are in a fixed ratio. Constituent elements are combined in a fixed ratio. While in a mixture, it can be different ratios as well. For example, I can randomly just add 50 grams of salt in water, and in another beaker I can add 70 grams of salt in water. Both will be a mixture of salt and water. So no fixed ratio of constituent substances. Alright, so that was all for mixtures and compounds. Now in this chapter we'll be dealing with mixtures. Alright, we'll be dealing with mixtures. So when we talk about mixtures, we actually have 9 processes that we'll be discussing, and we'll be discussing how to do these processes and when to do these processes. So let's just move on. So yeah, as I was talking about the processes, first of all, the process we have is dissolving, filtration, and evaporation slash crystallization. Now, dissolving, filtration, and evaporation slash crystallization. Okay, next we have sublimation, then we have decanting, and centrifugation. Now, decanting and centrifugation are not as such part of your syllabus, but these terms have appeared in MCQs, so you should know what these mean. That's why I'll be covering them. Next is distillation. Distillation. Then we have fractional distillation. Then we have crystallization. Then solvent extraction. And finally, chromatography. Alright. Now, what do you need to know in all these processes? So, first of all, you need to know when to perform these, when to do, and then how to do it. For all these processes. And we ask you these in your exam. We only ask these 2 aspects in your exams. Alright, so first of all, dissolving, filtration, and evaporation. So let's just say that I have a solid. Let's say it's solid 1. Solid 1. It's soluble. And we have a solid 2 that is insoluble. And I mix them. For example, this was a petri dish, this was another petri dish, and in this I had NaCl, in this one I had for example barium sulfate. Now NaCl is soluble, barium sulfate is insoluble. Now while let's just say during transportation I actually spill some of this inside of this, but I need pure samples. So what should I do? Then I'll perform this technique: dissolving, filtration, and evaporation. You should add slash crystallization, and I'll discuss why. Alright, so we have NaCl and barium sulfate. So what do I do? First of all, I'll add water to the mixture and stir the mixture. Alright, so let's just say step 1: add water to the mixture and stir. So what will happen? You need to write this down. NaCl dissolves while barium sulfate remains suspended. Remain insoluble or suspended, you can say. Remains insoluble. Alright. So I added water and NaCl dissolved inside of the water and barium sulfate remained insoluble. Alright. Then what will I do? So what I do is I filter the mixture. Now be very careful in using your wordings here. It will be referred to as a mixture, not a solution, because barium sulfate is insoluble and it is suspended inside of it. So filter the mixture and barium sulfate, and you need to tell what happens. So barium sulfate will remain on filter paper. On filter paper, while NaCl solution passes as filtrate. While NaCl solution passes as filtrate. Now there are a few terms I want to familiarize you with. So this is filtration, filter funnel. All right. This is a beaker. And this is the filter paper. All right. So this is the filter funnel. This is the filter paper. All right. This is a beaker. When I add the mixture, the substance remaining, it's known as residue. The solution that passes through, it is known as filtrate. Alright, you need to be able to distinguish between these terms because I'll be using them. Great. Now next step. Now what is the next step we should do? So I washed the barium sulfate that is collected on the filter paper. Why? Because there might be some NaCl particles that might be left, or might be stuck along with the barium sulfate. So I wash the barium sulfate crystals under distilled water. Alright, why under distilled water? Because tap water contains impurities, so I want a pure sample. So I wash the barium sulfate crystals under distilled water, and I want pure and dry sample. So what I do is that I dry the crystal under fold of filter paper. All right. So what you write is that wash the barium sulfate crystals under distilled water and dry the crystals under fold of filter paper. Great. Next, what do I do with the NaCl solution? Now do remember that I had the NaCl solution inside the beaker. as filtrate. So what I do is that I heat the solution till saturation point. And some students ask that how do we get to know that saturation point is achieved? So all this is done in a machine. It's a calibrated machine, so it does know when the saturation point is achieved. So I heat the solution till saturation point, or you can also say crystallization point, and then I cool it at moderate rate. All right. So what will happen is that crystals will start to form. NaCl crystals will start to form. Now I filtered the NaCl crystals and then dry them under folds of filter paper. Now we cannot wash NaCl crystals because they are soluble, and then we'll be missing the whole point of the exercise. So all this I have written is actually crystallization. So that's why I asked you to write crystallization. So what happens is that we say that heat the NaCl solution until saturation point, right? And cool it at moderate rate. So crystals will start to appear inside the beaker, and then what I'll do is that filter off the crystals the crystal and dry under folds of filter paper again, and dry under folds of filter paper. Now there is an alternate thing that we can do, and that is heat until all the water has evaporated, and what I'll get is NaCl crystals. And in that case you do not need to actually dry them because they'll already be dried because I have evaporated all the water. So another thing that you can do is that heat the NaCl solution until all the water has evaporated. Collect the pure dry NaCl crystal. Great. Now, when we have the option of evaporation, which is, as you can see, far more easier, why do we carry out crystallization? I need you to think about it. Just give it a thought. Okay, I hope you have reached your decision. So why do we do crystallization? So when I want you to collect a hydrated salt, for example, if I ask you to collect copper sulfate dot 5H2O. Now because of this 5H2O, the salt will now be referred to as hydrated salt. So if I ask you to collect copper sulfate dot 5H2O, then if you heat copper sulfate dot 5H2O until all the water has evaporated, then this copper sulfate dot 5H2O will break down into copper sulfate plus 5 moles of water in form of steam. So, alright, now it's better for you to learn these colors as well. Copper sulfate dot 5H2O is blue and copper sulfate is white, dry copper sulfate. Alright, so If I ask you to collect hydrated copper sulfate, then evaporation will be hazardous because you've just evaporated all the hydrated part of the salt. So first of all, when the salt is hydrated, and second of all, when salts decompose on heating. All right. So whenever you find a salt that decompose on heating, you actually do crystallization instead of evaporation. So some students ask that how do we know that whether a salt decomposes or not, and this you will only be able to judge when you have done metals chapter. So until and unless I have done metals chapter with you, I'll be telling you myself which salts decompose on heating and which not. But for a safer side, let's just stick to crystallization. Always try to perform crystallization unless specified by the question. All right. So you'll be on a safer side. Okay. So when do we do crystallization? So the question was when to do crystallization. You can do it in any situation, but what are the specific conditions that make it mandatory for you to do crystallization? So first of all, when you are to collect a hydrated salt, or you are to collect a salt that decomposes on heating. Salt decomposes on heating. All right. Now I did filtration in this whole process. But filtration is usually very slow process. It takes a lot of time. So you need to be able to know ways to increase the filtration rate. Alright? Just think about it for a moment, pause the video and try to jot down some points that you think might be able to increase the filtration rate. Just pause the video. Alright, I hope you have thought about it, and let's just see how we can increase the filtration rate. Okay, so first of all, you can stir the mixture that is over the filter paper. Alright, so stir the mixture over filter paper. Now what that does is, for example, this is the filter paper. Now it has gaps for particles to pass through. Some particle may be stuck here, for example in this space. So when you stir the mixture, the particles start to flow and they do not get stuck here. So it keeps the flow maintained. Alright. Now the second step, use a fluted filter paper. Use a fluted filter paper. Fluted filter paper is that has been folded. All right. Now let's just say like this. Very bad drawing. Very bad drawing. All right. So what that does is increases surface area. Increases surface area. Next, you can also use a suction pump. Now what a suction pump will do is that it will establish a gradient. Alright, use a suction pump. And fourth, attach the stem of filter funnel to the walls of the beaker. Now what does that mean is, for example, this is a filter funnel, this is a beaker, you place it like this. Now what that does is it actually creates a flow. Alright, when this flow is created, it actually fastens up the process. So what you'll say is what you'll say is attach stem of filter funnel to walls of beaker. Great. Next, I want to tell why to actually cool the solution, the heated solution, at a moderate rate. Why not at a faster rate, and why not at a slower rate? So, why cool at moderate rate? Why cool at moderate rate? Why not at a faster or a slower rate? Alright. So what will happen if I cool it at a fast rate? Very small crystals will be formed. Alright. So what makes that difficult? What makes that unfeasible? So when small crystals are there, it is difficult to filter them off. So you'll get the crystals here in the solution. They'll be like this, and you need to filter and you actually need to filter them off for to use them actually. So if you use if you cool it at a moderate rate, very small crystals will be formed. But and that creates the problem to filter them off. So small crystals formed that are difficult to filter off. And what will happen at a slow rate then? Just give it a thought. So when I actually cool at a slow rate, large crystals will be formed. Now the problem with large crystals is that water is trapped inside the crystals, making them impure. So large impure crystals formed. Large impure crystals are formed. Alright. So when I talked about crystallization, alright, I needed to mention a thing, and that was that crystallization can only be done on a saturated solution. Alright. So first of all, you need to know that how to make saturated solution. Now I'll be discussing this in the crystallization technique as well when we do it specifically. So how to make saturated solution, but I actually want to address it here as well, that why do we actually heat it? How to make saturated solution? Either I add excess of the solute, or I can evaporate the excess solvent. So either add excess solute or evaporate excess solvent. So we have a limited amount of solute because we have actually made a mixture and we want to separate the two salts. So what's the next feasible option? It is that we evaporate excess of the excess solvent. So when we heat the solution to saturation point or crystallization point, what we are actually doing is that we are evaporating excess solvent, and when we evaporate excess solvent, we are making a saturated solution. And remember it as a fact that crystallization can only be done on saturated solution. All right. Now that was it for today's class. It has been a long class. All right, so next we'll do other processes, that is sublimation, centrifugation, decanting, and solvent extraction, etc. So until then, I hope you're enjoying and see you soon. Bye.